Welcome back, Physical Science 20. This is PW2.4, plane mirror reflection. So we've looked at reflection, various types of media. Now we look at how it reflects off a plane mirror. So we'll look at law of reflection, distinguish between specular and diffuse reflection, investigate image formation in plane mirrors by constructing ray diagrams, identify the properties including type, whether it's real or virtual, attitude or orientation, which is upright or inverted, magnification, is it smaller, larger, or same size, and position relative to the mirror surface or vertex of images formed in plane mirrors. Almost 4,000 years ago, Egyptians understood that reflection requires smooth surfaces. They used polished metal mirrors to view their images. Sharp, well-defined reflected images were not possible, though, until 1857. However, Jean Foucault, a French scientist, developed a method of coating glass with silver. Modern mirrors are produced using ever-increasing precision. They are made with greater reflecting ability by the evaporating of aluminum or silver onto a highly polished glass. The quality of reflecting surfaces is even more important in applications such as lasers and telescopes. More than ever before, clear reflections in modern optical instruments require smooth surfaces. So looking at the law of reflection, what happens to light that is striking this paper or this video? When you hold the book up to the light, you see that no light passes through it. Recall from earlier that an object like this is called opaque. Part of the light is absorbed and part is reflected. The absorbed light spreads out as thermal energy. The behavior of the reflected light depends on the type of surface and the angle at which the light strikes the surface. Recall from earlier that when a wave traveling in two dimensions encounters a barrier, the angle of incidence equals the angle of reflection of the wave. This same two-dimensional reflection relationship applies to light waves as well. Consider what happens when you bounce past a basketball. The ball bounces in a straight line as viewed from above to the other player. So if you look over here, it's very similar to this. Light reflects in the same way as a basketball. The figure on the right, or on the previous page, shows a ray of light striking a reflecting surface. So you have this normal, which is, so where it hits the surface, you have a line perpendicular from that surface, and it reflects in such a way that the angle between the incident light ray and the normal is equal to the angle between the reflected ray and the normal. The normal is an imaginary line that is perpendicular to the surface at the location where the light strikes the surface. The reflected ray, the incident ray, and the normal to the surface always lie in the same plane. So this, you can imagine this as a flat surface as indicated by this rectangular shape, indicating that it's all on the same flat surface or plane that we say in math. Although light is traveling in 3 dimensions, the light reflection of light is planar, i.e. 2-dimensional. The planar and angle relationship are known together as the law of reflection. So the angle that a reflected ray makes as measured from the normal to a reflective surface equals the angle that the incident ray makes as measured to the same normal. So angle I equals angle R. Sometimes I just simply shorten that to be angle I equals angle R. And then lastly, they must lie in the same plane. So the incident ray, reflected ray, and the normal are all in the same plane. All right? So we have angle I equal angle R. It works in bounce passes, cool, and also wave reflection and light ray reflection. If we look at smooth and rough surfaces, consider the beam of light as shown in figure A below. Now it's kind of hard to see here, but it's going along a flat surface. Angle, if I was to draw a normal here, angle I equals angle R. Okay, you can't really see that, but it's kind of, the photocopying is kind of dark. All the rays in this beam of light reflect off parallel to one another, as shown as in parallel in figure B. So showing that, you can see that if I was to make a bunch of light rays parallel, they reflect off parallel because this is a flat surface. This occurs only when the reflecting surface is not rough on the scale of the wavelength of light. Such a surface is considered to be smooth relative to the light A smooth surface such as a mirror causes specular reflection, which is, we could say it's almost like regular reflection of how we would perceive it. So parallel light rays coming in are reflected parallel. Okay. What happens when light strikes a surface that appears to be smooth but is actually rough on the scale of the wavelength of light, such as the page of this textbook or a white wall? If we look on the next page, we'll see that, in which light is hitting a piece of paper. So if you look over here, all the light rays that make up the beam are parallel before striking the surface. So parallel, 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 just like the other one. But the reflected rays are not parallel. So this is called diffuse reflection. So reflection due to a rough surface. But the law of reflection applies to both smooth and rough surfaces. For a rough surface, the angle that each incident ray makes with the normal equals the angle of the reflected ray. So you have to treat each ray separately. So here you can see angle I equals angle R. Over here you can see angle I equals angle R. Angle I, angle R, angle I, angle R. So for each individual light ray, the law of refraction holds, but together, due to a rough surface, they don't necessarily have the same incident ray because of how they hit that rough surface. So however, on a microscopic scale, the normals to the surface locations where the rays strike are not parallel. So normals are not parallel. Thus, the reflected rays cannot be parallel to each other. The rough surface prevents them from being parallel. In this case, the reflected beam cannot be seen because the reflected rays are scattered in different directions. So if your eyeball is over here looking at this, it's very difficult for all those rays to reach your eye, as opposed to the other diagram where they all reflect off parallel to each other, and that can hit your eye. With specular reflection, as with the mirror, you can see your face, but no matter how much light is reflected off a wall or a sheet of paper, you can't use them as mirrors because all of those rays are not reflecting parallel to your eyeball. There's just simply not enough rays to see. Objects and plane mirror images. If you looked at yourself in a mirror this morning, you saw your reflection in a plane mirror. Plane mirror is a flat, smooth surface from which light is reflected by specular, so regular reflection. To understand reflection from a mirror, you must consider the object of the reflection and the type of image that is formed. An object is a source of light rays that are to be reflected by the mirrored surface. An object can be a luminous source, such as a light bulb, or an illuminated source, such as you, a girl, etc. So light hits your face, then it hits on the mirror, so that's considered to be the incident ray, even though technically the incident ray is a reflected ray of something else. Most objects that you will work with are a source of light that diverges or spreads out from the source. Consider a single point on a bird in the figure on the next page. Light reflects diffusely from the crest of the bird, the object point. What happens to the light? Some of the light travels from the bird to the mirror and reflects. What does the guy see? So if we take a look at the next page, so the sun hits the bird, and some of the rays reflect off, and they become the incident rays of the bird, and they reflect off and hit the boy. Because his brain processes this information as if light traveled in a straight path. So yes, our brains tend to process information as if light is traveling a straight line. So he may get confused and think that the bird is somewhere behind here. Quite often that's why birds fly into windows, because they'll see the reflection of a tree over here and they assume that, oh, light travels in straight lines, the tree is right there, but actually it's a reflection off of a window. Now, so it seems to the boy as if the light had followed the dashed lines back here. So seeing the eye of the bird, followed the dashed lines in behind the mirror, it appears like it's coming behind here. So if you look in your mirror reflection, you of course know it's a reflection, but it appears that you're on the other side of the wall. So it seems to have come from that point over there. The boy in this figure sees rays of light that come from many points in the bird. The combination of the image points produced by the reflected light rays form the image of the bird. This is said to be a virtual image, which is a type of image formed by diverging rays. So rays that are spreading out, that's what we get from. A virtual image is always on the opposite. This is a key thing to note. You can put a little star here. So a virtual image is always on the opposite side of the mirror. So it seems to be behind the mirror. The images of real objects produced by plane mirrors are always said to be virtual. Eventually, when we take curved mirrors, we'll see that there are real images. And the difference there is that real images you can pick up on a screen. Like if I held a piece of paper, I'd be able to see the image. Whereas here, no matter where I put a piece of paper, I would not get that image of the bird on the screen. That's kind of another way, but we'll see that later on. Properties of plane mirror images. Looking at yourself in a mirror, you see that your image appears to be the same distance behind the mirror as you are in front of the mirror. That's another thing that's true. How could you test this? Place a ruler between you and the mirror. Where does the image touch the ruler? You also see that your image is orientated as you are, and it matches your size. This is where the expression of mirror image originates. If you move toward the mirror, your image moves towards the mirror as well. If you move away, your image does as well. So if we look down here, image position and height. So here we have a candle. The geometric model of the figure below demonstrates why the distances are the same. So if you take a look here, DI is distance of image from mirror, whereas DO is distance of object from mirror. And I think we'll stop there. We're almost at the time here. We're over 12 minutes, so we'll continue on with this when we get back.